If you, so try and, yeah, we're going to try and focus. Come on. Hooray! Today we are going to learn all about mirrors and lenses.
Is that why you have that out?
Everything you've always wanted to know, but we're afraid to ask.
Is it too cool?
Somebody's having a wild party. Sure. Get to a fight if you have to. First, we're going to talk about mirrors, and a mirror, of course, is something. It's a piece of glass or plastic designed to do what? Reflect. So,
If those are my scissors.
yeah, that would go in your nose.
Jose.
So a mirror is a piece of glass or plastic designed to reflect light in a particular way, and we have three useful shapes of mirrors. There's also other shapes that are just kind of fun, but the most useful shapes are, the one you use the most often is a flat mirror or a plane mirror. The word plane means flat. An airplane flies flat through the air instead of in a parabolic trajectory. That's why it's called a plane. Interesting trivia, right? Okay. Anyway, but a plane mirror, of course, this is the one that you stumble out of bed and stare at yourself and say, "Good morning, beautiful." And you probably noticed that your head looks normal sized in the mirror, right? You don't look at yourself and say, "Oh my goodness, I have a huge head." Or you don't say, "Look, it's a little pink head." You're normal looking, but you're reversed. So when I stare in the mirror, I am right-handed, but mirror me is left-handed. He's weird like that.
He just likes to mess with you.
Anyway, a plane mirror can only form a virtual image, and a virtual image is always erect. A virtual image is an image that you can only see if you look into the mirror or into the lens. You can't see it reflected on the wall or something like that. So a virtual image is always erect. Erect means upright. So you walk in an erect fashion. You don't crawl like a dog. A real image is the opposite of a virtual image. A real image is one that can be focused on a screen, and a real image is always inverted. Now, if it's inverted, that means it's upside down. So a real image we can focus on the screen. So here on the screen, guess what kind of image we have? A real image. We can tell that because it's focused on the screen. So that means if you would stare into the Iki there and go blind, what would you see? A little thing upside down in there, because that has to be upside down so that it appears right side up here. So there's a little computer screen in there that's about this big, and the light is shining very brightly through that computer screen and projecting a nice real image over yonder here. Hooray. So a real image we can see on a screen. A virtual image can only be seen by looking into the mirror or lens. And so you don't see yourself until you're looking into the mirror. You don't say, "Oh, look, here I am on the wall," bounced off the mirror. It doesn't happen like that. You have to actually be staring into the mirror to see your nice little virtual image. So we did a lab on virtual images the other day where we made a little thing, and ideally you found that most of you were not googly-eyed, and the distance behind the mirror looked like the distance in front of the mirror, which hopefully you've noticed. Like if you're a foot on this side of the mirror, then mirror you is a foot on that other side of the mirror. If you bring your face close to the mirror, he brings his face close to the mirror, and yeah, that sort of thing happens. So that's a virtual image. How pretty. The second mirror type is called concave, and a concave mirror is curved in at the center. These are called converging mirrors because light rays coming in will converge on a point called the focal point. Isn't that pretty? So a concave mirror, it's going to be curved in at the center, so the shiny side is here in the middle, and it's got this line running down the middle, and this line coming down the middle is called the principal axis. But what happens is any light ray that comes in parallel to the principal axis is going to hit the mirror at a different angle because this thing has a shape to it. So what happens is there's a different angle. That was beautiful. Different angle corresponding with each of these. And, okay, we'll pretend I drew this on the principal axis. They all converge on one point. So that point is called, of course, the focal point. It's focusing all the light on this point. And of course, that point could actually be on the principal axis. Now, I can't draw today. The opposite of this, of course, is that any light source that's placed exactly at the focal point is going to bounce off the mirror and reflect out in a straight parallel beam. How would this be useful?
Lasers.
Simpler than that. Yes. Have you ever looked inside of a flashlight before?
Yes.
Yeah, if you looked inside a flashlight, you probably noticed that there's a little mirror inside that's all shiny and curved like that. And the light bulb is right here. And why is the light bulb right there? That's at the focal point. So if it's at the focal point, then all these light rays... Hey, stop that. Okay, try that again. So all these light rays that bounce backwards and hit the mirror are all going to bounce out in nice straight parallel lines. So you say, hey, that gives me a nice beam of light. If you've ever looked inside your car's headlights, there's also a little concave mirror behind it for the same reason. You want all this stuff to come out like this. Searchlights work the same way. It's all trying to focus that beam real nicely. Flashlights, though, have you ever noticed that when you shine a flashlight, you have, if you have something close to it, you've got this nice bright beam of light that's in the middle here, and then you've got a thinner beam that's out like this, and then when you bring your flashlight out farther, this hasn't gotten much different, but this one spreads way out and gets super big and dimmer and dimmer and dimmer. Okay, I'm not the only one that's noticed this. The reason for this dim one that starts off close and moves out when you move it out is because some light rays, of course, are going out from the front. And the ones that are going out from the front, are they focused in some sort of beam? They're just scattering. So this gets wasted as light, and really this is only the good light. So all the light that goes back is good light, but all the light that goes forward is just kind of wasted, really. So what your car headlights have started doing to make your car headlights more efficient is they stick a mirror right here. So all the light ray that was going out forward that would get blocked is going to bounce back off of the mirror and then of course come out and make that even brighter. That's a cool idea, right?
Yes.
Yeah, I like that. I always like staring at new things and saying, hey, that was a clever engineering. Okay, concave mirrors are the most versatile of the mirrors because there's a lot of different ways we can use them. Flashlights is one way, but there's a lot of other stuff that's kind of cool. So we can make a lot of different image types depending on where we put stuff. So I'm going to give you a moment so you can copy all these words in, because I mean like that, and make you actually write words down. Jeopardy fan.
We know Jeopardy. We just figure it out instead.
Yeah.
Okay.
And then you write all of that.
So he's very
Okay, so where do we find our magic breakpoint here? Notice that everything on this side is, and everything on this side is, and where is our magic breakpoint there?
between the
At F. Now you're saying, what the heck is F? Well, if this is our mirror and this is my principal axis and this is my focal point, focal point is F. So the distance from here to here is the focal length. That's what we call that. So if we put our image somewhere over here, if your little smiling face is going to be right here, we're inside of F. So if it's inside the F, what happens is you're going to be big, you're going to be right side up, but the only way you're going to be able to see this is by staring into the mirror. On the other hand, if I move it past F, now suddenly I can get real images. And so that's cool. So anything between F. But then if we double this distance, we make it twice that bigness, then we get 2F. So we have F, and when we have 2F, and 2F of course is just twice what F was, so this distance, that's, pretty easy. So if I get this somewhere between F and 2F, it's going to get bigger. Well, the closer I am to F, the bigger it's going to be. So over here your face would look gigantic, over here your face would look exactly life size, and we get over here and your face looks tiny. So it depends on where we put it in respect to the F and 2F relationship. Except all the real images, of course, are going to be, which means really your face is going to look like that. Hooray! This make sense? Yes, that's very, very pretty. So now we'd like to actually draw a ray diagram and show you where these images form. So if we draw a ray diagram, we've got some room there. So you're going to draw your mirror and you're going to draw your little principal axis. And you're going to pick some point and call it F, and then pick like twice that far and call it 2F. Excuse me. So if we start off like this and I make an arrow, this arrow is going to be my object, so I'll call it O. And we want to know where the image is going to form. Well, there are two rules to follow when you're making a ray diagram. A ray diagram is just you're drawing these nice little straight lines. We won't use a ruler and make them perfectly straight, but we can still get the point. Any light ray that came in parallel to the principal axis, we said it has to go through. Remember, all the light rays that came in parallel all converged on the focal point. So any light ray that comes in parallel here is going to bounce back through the focal point. But we said the converse of that was also true, so any light ray that goes through the focal point is going to hit and bounce out parallel. Now, do the light rays cross? Clearly the light rays cross. So where the light rays cross, this is where the image will form. If I hold a piece of paper here, it'll be blurry over here, and it'll be blurry over here, but it'll be sharp right here in the middle. But I was picking this off the tip of the arrow, which means the tip of the arrow is now here. So this is where my image forms, and of course, look, my image is inverted. It's also bigger, which is what we said would happen if the object was between F and 2F. Isn't that kind of cool? It almost like matches reality or something.
Mrs. Ford,
We are right here.
because I haven't got to lunch.
Why don't you get out of here?
I was just coming to pick up the word.
Okay, you can hear yourself complaining if you shout louder.
What do you want? Say hi, future me.
Hi.
There you go.
Is there any word training?
Problem C is what we're going to do after all this is done. Have a wonderful weekend.
You too. Bye. Bye, guys.
Bye, everyone.
Bye.
Bye.
Yeah, say bye to your
Thanks for
future
leaving.
self. Say bye to your future self. Oh, bye, future self.
Bye to you.
Right.
Oh, yeah.
Okay, do we need to draw another ray diagram? Is that good?
That should be good.
It's
Yes, dear.
Is the second arrow, is it supposed to be after tulip? Like,
Well, it kind of depends on where you put
oh,
your thing here. So it'll definitely show up farther away than this one did because it got bigger. Okay then,
What is that? Is that J or an I?
that's an I for image,
I see.
and now it's gone. Okay, our third mirror shape is called a convex mirror, and a convex mirror is curved
Outward.
outward at the center like a pregnant woman's belly,
Like a magnet.
or sadly like my belly,
Or a dead body.
or a dead, well, okay, if you want to be
It's a state. It's a certain
morbid
stage of
about
decay.
that. Yes. These are called diverging mirrors because the light rays spread out. Concave mirrors, did we talk about them being converging mirrors?
yes.
I wrote that down, but I didn't talk about it. Okay, for concave, what happens is, again, the light rays that come in parallel are all going to come together at that focal point. So if things come toward each other, we call that converging. On the other hand, a convex mirror bounce out this way, so any light ray that comes in parallel here is again going to hit things at funny angles. So these are going to, well, that one's going to bounce straight, but these are going to bounce farther out. So now the light is spreading out, and that is called diverging. So converging is coming together, diverging is spreading apart. So if you have something that's converging, I can focus that light on a point and make this a very bright light. If it's diverging, it'll actually make it dimmer. It'll make it weaker. So, yeah. I want to be divergent. Okay, anyway. Diverging mirrors, again, are convex. And these can only form one type of image, so they're really boring. The only image they can form is virtual, which means you're going to be right side up, and you're going to be smaller. See yourself, how are these valuable? Well, they're valuable because we can see over a much wider area than you normally see. And so you see over a bigger area, but if you think it's a plane mirror, then you think, oh, that's farther away because it's smaller, and it's not really, and then you kill somebody. If you've ever been to a hospital, it's kind of cool. If you're at a hospital and there's like, you're running down this direction and you want to, you have somebody on your little bed and he's dying and you got to take him into the emergency room. And you're running this way, but you want to make sure you don't smash into somebody coming around the corner. What they have is, these big curvy mirrors that are up on the ceiling here. And when you're running this way, you can actually see very easily down that way or down that way or all different ways. And everybody looks funny, but, it's real helpful to know if I need to scream or shout and get people out of the way, or if I can just run down the aisle. We have these also in your
Stores.
Spoons?
Yeah, I was gonna say your car. Okay, how many people have been in a car before?
I've only been in
Good.
cartoon
How many people
wagons.
have actually sat in the driver's seat?
Me.
Good. When you're sitting in the driver's seat, you got two mirrors that are about this far away from you.
Oh, and they have a little warning.
And then you got another mirror that's way over there.
Yeah.
So these two are this far away from you, and those are nice flat mirrors, and you just see what you see, and everything's what you expect to get. But the one over here, the problem is that one is like 2 or 3 times farther away from you than these other mirrors are. So for you to be able to see the same amount of stuff, the mirror over here would have to be gargantuan. And nobody wants a 4-foot right-hand mirror hanging off their car. That would look weird. It would just upset the balance of the car tremendously. So we don't have this huge mirror over here. What we do instead is we have a mirror that's like this. It's convex, it's curved. And so then you see over a wider angle, so I can have the same size mirror over here, but I can still see as if it was a closer mirror. I can still see the same amount of stuff, but the problem is, again, everything is smaller. Now, when I look at Iran's face, it looks big, and when I look over at you guys, you look like you have tiny heads. I can squeeze Julie's head. So I don't say, oh look, Julie has a cute little head. You say, oh, Julie's head is farther away, so it looks smaller. Same thing, when you look in that mirror, you don't say, oh, what a cute little Jeep. You say, oh, that Jeep must be way the heck back there, but it's not really. That's why they put a little warning on there that says, objects are closer than they appear. And that's really saying it's really bigger. This mirror's making it look smaller.
Some mirrors also have some side mirrors also have a second mirror attached to cover blind spots.
Yes, and that's even more convex, so it sees over a much bigger area. Now, I'm going to show you two mirrors. This first one is
Concave.
concave. It's curved in at the middle, and first when you look at it, my hand here is inside F, and so my hand looks huge. It also looks right side up. Now, but when you look at yourself in this mirror, you look upside down. Freaky, right? I first saw one of these mirrors when I was a little kid.
We're eating
They
fish.
had a mirror just about this size that was in a stand at this glasses place. And my older brother, he needed glasses when he was like 5. Poor little thing, right? It was horrible. He got glasses, and then he came home and he was looking out the front window and he said, hey, the people across the street are moving. And my parents said that there was some sign that was like enormous in their front yard that said for sale, and it had been there forever, and the kid had never seen it. So, poor little blind boy. Anyway, so while my parents were there getting glasses on him, I saw this mirror, and I thought it was really cool because, you know, you're staring at it with your face up here, and it's like, whoa, what a huge face, you know, but then I'm running around the store, and I see myself from a farther distance, and it was like, whoa, I'm upside down. And of course, when you're a little kid, that's really, really cool to see yourself upside down. So then I'm walking closer and closer to it, you know, and then all of a sudden I get some spot where I can't see myself. And then I walk a little closer and I'm right side up again. So that part where I couldn't see myself, that was when I was right at F. Yes. So I'm going to bring this around so you can see yourself inside F. And see,
I want to eat
Oh, God.
I want to eat fish on that mirror.
I saw it.
It's, I always wanted to try seafood. It looks so weird.
I always like
My worst nightmare.
Oh, have you seen that?
your typical adolescent reaction is to like,
No, my typical kid reaction is, what the heck is the proportion on that weird creature?
That was such a
I love this shot.
In terms of reaction.
I always look at this and say, how do you get that much good looks in one spot? But no, when you're older, you stick this in front of any person that's older, and they're just like, yep, that's me, all right. But you stick it in your typical adolescent, and they're like, no,
No,
and they're
'cause
cringing.
Because it reminds me of the typical drawing that fantasy artists usually make of.
Yeah, the caricatures.
No, not caricatures exactly, but you know, sometimes they have those overs in the things that they're really thick, like the heads are
Yeah.
large and their necks are really huge.
That's usually the caricature.
It's the proportions that got me.
Yes. Okay, this one is
Convex.
convex. It's curved outward. Now, if I put my hand in front of it, it's still upright, and you guys way out there are still upright. The only thing we can make is this is smaller vertical. See how my hand is smaller? But the advantage here is
You can see more.
you can pretty much see everybody in the room, right?
I can see the whole room.
Yeah, so it's nice because of that. We have these up in the library, and that way the librarian can be at her desk and look and see if there's somebody hiding in the stacks over there.
Hey.
So
Looks like a cool selfie.
yeah, it's a cool selfie.
So
So you've seen these in stores and stuff, and yeah,
You're not gonna pass it around.
you've seen them. It's not as exciting as the other one.
Yeah, it is. I want to see what my face looks like up close on that one.
You already saw it on the other one.
So it looks about the same, mostly.
Okay, yeah. So of course there's math involved in mirrors,
Ah, come on.
and we have the mirror formula. And the mirror formula says 1 over F is 1 over I plus 1 over dou. F stands for the focal length again, and again the focal length is that distance from, where is F? This is the focal point, but this distance from here to here would be the focal way. That make sense?
Yeah.
So the focal length is what goes in here. And then the distance to the image and the distance to the object, again, are measured from the mirror. So if I had my object was over here, then this would be the DO. And when that image formed over here, this would be my DI. Hooray! That's so pretty. There's also a magnification formula, and that says high over ho is di over do. And that equals the magnification, which tells me that I can either use high over ho or di over do to tell me how much bigger it gets. And so high, of course, is the height of the image, and ho is the height of the object. And so this will give you a number like 3.2, which means it's 3.2 times bigger. So you say, hey, my face looks huge. How much huger? You can figure it out using this formula. And of course, this is also useful for if I know 3 out of these 4, I can just figure out the 4th one. Easy, right? And yeah, this one always sounds like you're one of the dwarfs or something. Hi-ho! Now we're going to switch to lenses. And lenses are very similar to mirrors, except instead of reflecting, these are going to
Focus.
Refresh.
Refract.
Very good. So these are going to refract light in a particular way, and we only have 2 shapes of these. We had 3 shapes of mirrors, but we only have 2 shapes of lenses because a flat lens we call a window. Yeah. So that's not exciting. So we still have convex and we still have concave, and convex still means curved out at the center, and concave still means curved in at the center, but they're going to act the opposite of what they were with mirrors. So in a mirror, a convex lens could only, or a convex mirror, could only form a smaller virtual image. A concave lens is the same way. It can only make a smaller virtual image. And just like that, a concave mirror was the one that was more versatile. I could form more image types. I can also make more image types with a convex lens. So they tend to be more important to us overall because we can do more things with them. A lot of things have multiple lenses in combination when you're dealing with funky things. But you may have noticed that there's a chart here that I didn't make you fill out a second time because I'm nice, because it's identical to the other one. And you're saying, really? Yes, a convex lens, again, acts exactly like the concave mirror did, so it's going to act the exact same way. So if I'm inside of F, it's going to be virtual and enlarged, and right side up, and so on down the line. It's going to be real if I'm past that, and we can make it bigger, life size, or smaller. So what we're going to do with this one instead is concentrate on how do we use these in real life. So if it's inside F, again, it's going to look right side up, but it's going to look bigger. When do I use a lens to do that?
Magnifying glass.
Hey! Thanks. Has anybody ever played with a magnifying glass before? Anybody ever noticed that they're fatter in the middle and skinnier at the edges?
Yes.
Hey, what do you know? And so magnifying glasses, again, if you're using it inside the focal point, then what happens is you I paused at just the right moment there, right? If you're using a magnifying glass inside the focal length, again, everything's going to look just right side up and real. And so it's just going to look bigger. And that's the way we use it if we're just trying to make something bigger. And so those come in real handy. My mom likes to do a lot of needlepoint and stuff like that. And she's always got this big magnifier that she has that it like has a chain that wraps around her neck, and then she has a piece that leans against her body, and then it's like here, and then she can do her work underneath that, and it's right there in that F range, and so she can do it, and
It looks bigger.
which is nice on older eyes. The older you get, you hate bright lights, and you don't like little things. if you put it exactly at F, what happens there?
Oh God. You don't see it.
You guys have done this before. Yeah, when you're moving it back and forth as a magnifier, have you ever noticed that there's like light that comes out the bottom and it gets smaller and smaller and smaller? And you get it down to a point? When you get it right to a point, that means you're holding it right at F. Now you don't see anything at that point, but it's really useful for starting things on fire. Did you ever try that when you were a little kid?
Oh,
No,
yes.
not
I was
into it.
allowed to play with fire.
I just crushed them.
But it's a
Okay, you guys would burn ants because you're a little sadists. You're mean. Okay, so what happens there is if you have your little magnifying lens, what happens is sunlight is coming down from here, and of course sunlight gets you nice and warm to begin with, but if I concentrate that much sunlight down to a point, I have this much sunlight concentrated 1,000 times, so suddenly it's 1,000 times hotter, which is why it gets nice and toasty, and you can char paper and start things on fire. And
Murder ants.
yeah, I was playing with a magnifier when I was in elementary school, and the sun was coming in the window, and I was burning paper, and I almost started my house on fire. I didn't know, man. I was a little kid. I was stupid. If we're between F and 2F, then what happens is I'm going to see myself upside down, but enlarged. When do we use a lens to make something that's upside down and enlarged?
Fun houses.
Come on, Trey.
Telescope.
Oh, I saw you stare at it, so I thought you were gonna say it.
Did I start it?
The projector.
Oh, yeah, I was thinking
At one time,
Oh.
you looked up and then you looked down, and I thought you were gonna say the projector, which totally would have been right. We use these for projectors. I told you a while back that behind that lens you're going to see a little tiny computer screen. And what do you see over here? A really big computer screen. So it's gotten bigger. And this is what happens is if you're between F and 2F, it's going to make it bigger. The closer you get to F, the bigger it gets. So if you go to the movies, there's a lens in front of the film. And guess where that lens and film relationship are? Between F and 2F, but it's really, really close to F because that film that they're projecting is about this big, and on the screen it's
huge.
yeah, OMG huge. So it gets very, very, very large there. So if you've ever, has anybody ever used a slide projector?
I think
Probably
maybe.
would have been back in elementary school when people used to still use those. Now everything's digital. So, but if you use a slide projector, the problem that people have is they look at the slide and then they stick it in and then they turn it on and everything's upside down. And they're like, oh man, I forgot. And you got to put your slides in upside down to make them go right side up because, again, it's a real image and real images are always inverted. So you got to do that. So if you go back and look at the movies that are actually being projected in the display booth, they look upside down, and then on the screen they look right side up. Now, what if we're at 2F? If we're exactly at 2F, then we want to make it life size. It's going to be exactly the same size. Where would we use a lens where we want something to come out exactly the same size?
Glasses. Window.
Your glasses actually depends on, we'll talk about your eyes later. A window isn't really much of a lens. There's one application that you guys use all the time, or you get at least the benefit of it all the time.
Snapchat.
And it, Snapchat. Has anybody ever used a photocopier before?
No, because ours are broken.
I use them all the time because I have to make these papers that you're writing on right now. So if you look at this, what happens is I put these things in the machine and it makes a copy of it. And then when that copy comes out, I have to throw them away all the time because when it comes out, they're all upside down. And I say, I can't use this. I'm joking, I don't throw them away. You just turn them over and they work fine. But if you've ever used a photocopier, you know that you put it down right side up, but they always come out upside down. And the reason for that is you're making a real image, so it's always going to be inverted. But if you've ever looked underneath the glass that the paper sits on top of, underneath the glass there is a lens. And so you've got that glass that's here, and down here there's a lens. And this lens is looking up at the piece of paper on top of the glass, and guess how far this distance is?
Very.
It's exactly twice the focal length of this lens. So if this is a 10 centimeter lens, then this distance has to be 20 centimeters to make a perfect size copy. Now, but sometimes you can make your photocopier bigger or smaller, right? And all they do is they move that lens closer or farther away, and that changes whether I'm going to make it bigger or smaller. Cool, right? But most of the time we make photocopies exactly at 2F. Now, what if we're beyond 2F? Then we want to make something smaller. When do we want to make a real image that's smaller? A microscope is actually using two lenses in there. One of them is making it bigger because it's between F and 2F, and then the other is magnifying that even more, and that's like this. If I took a picture of you with my camera, your whole body could fit on the little sensor that's in the camera. Is the sensor bigger than you or smaller than you? Smaller than you. So that means I must make you smaller. So most cameras are beyond 2F because you're going to get smaller on the little sensor back there. Then, yeah, it used to be film. I don't know if you guys have heard about this in history class. But I'm joking, but yeah, they used to have things called film that we would make images on, and now it's all digital, which actually is so much better. It's so much better. But there's another thing that we use all the time that makes things smaller, that makes a real image. And I'm rubbing mine right now. Hey, yeah! Inside your body, you have a little camera too. Your eye is focusing on the retina. And so in the back of your eyeball, in the front of your eyeball, you've got this lens that's up here, and in the back you've got this retina. This is the screen where your image formed. And so this is focusing back here on this screen. Now, I'm looking out at the room, and how much of the room do I see? Pretty much the whole room. So if I can stick this whole room on my retina, which is like half a centimeter big, I'm thinking I gotta shrink it somewhat, right? So we're definitely well beyond 2F. Now, have you ever been staring somewhere and you saw something in your vision that's like slowly floating down? And then you move your eye to look at it and it goes jumping up and then it starts to slowly float down again. What you've got is a little tiny piece of something or other that stuck itself onto the front of your eye. And if it stuck itself on the front of your eye, it's just riding on your tears, that you always have a little tear coating on the front of your eye. And so it's riding down there, and then when you move it, it jerks up and starts coming down. But if it's right against your lens, then it is inside F, and it's acting like a magnifying glass, which means you're seeing that little piece of whatever
Big.
And so that's why it always looks like it's about this big. In reality, you practically need a microscope to see it. Very interesting.
Oh, wow.
Yeah. Okay, so this is how we use that stuff. And of course, we have ray diagrams here, but the ray diagrams here are a little different than they were with the mirrors. So we still have a principal axis, but this time, all the action's happening on both sides because it's going through it instead of bouncing off of it. So here we have a mirror, and on both sides of the mirror we are going to have an F, and of course twice that distance we're going to have 2F. So again, we're just going to approximate here. But if I have my object over here, and I put my object right at 2F, it should form on the other side right at 2F. And again, since we're just approximating here, it's not always going to work so well, but any light ray that comes in parallel to the principal axis is going to go through where? Anything that comes in parallel will come, it gets focused on the focal point, so it's going to refract through the focal point. Now, in reality, the bending does not happen in the middle of the mirror. We get some refraction right here, we get some more refraction here, and there's a straight line that goes in here, but it's just easier mentally to say, I'm just going to cause the bending right in the middle. So we get that. And again, the converse is true. Any light ray that comes through the focal, that was almost through the focal point. Any light ray that goes through the focal point and hits the lens is going to be refracted out parallel to the principal axis. And again, my light rays converge. That means there's going to be a place where I can focus. And ideally, you should find that your image over here forms right at 2F on the other side and is about the same size that the object was over there. And again, if we took the time to draw these more nicely, we would get better results, which we will do on Monday when we're doing our lens lab, which you'll like a lot. So make sure you show up on time on Monday or I'll lock the door, because it's going to be dark inside. So we can do our lens lab. And that's the day where you lock the door and 130 people will come and knock on the door. Because you can't let any light in. And so Murphy's Law says this is going to be the day that the most people in the universe will come visit you. Any questions on the ray diagram? Now, we also have a lens formula, but the lens formula is the same as the mirror formula, and also the magnification formula. So 1 over di still equals 1 over dou plus 1, 1 over di plus 1 over dou equals 1 over f, and di over dou still equals high over ho. So those still work great. So we're going to try a practice problem here. We have an 8.9 centimeter lens, 9.1 centimeters from a candle with a 3.2 centimeter flame. How far away is the image forming? We also want to know how big does it look on the screen that's placed there? And I didn't want to go that far. Bad me. There. So, first thing, of course, is to label our numbers. Find out what we got. So, one thing to check is that all of them are in the same unit. I don't really care what that unit is as long as they're all the same. But I could give you some in millimeters and some in centimeters and some in meters, and it wouldn't matter which one you switch them to as long as they're all the same. In this case, they're all the same. Now, if I have a word stuck to the word lens or mirror, the number that is stuck to the word lens or mirror is always the F. So if it's 8.9 centimeter lens, that's the focal length of the lens. If you see me take pictures, I have a big lens on my camera, and it's a 80 to 200 millimeter lens. What is this telling you? The focal length. It's a focal length that can shift between 80 and 200 millimeters. So depending on how you shift the lens around inside. But that's telling you what the focal length of the lens is. Okay. So here it says the lens is this far away from the candle. Well, the candle is my object. So if the candle is the object, that's the O, then this must be the, again, we're going to measure from the lens to the object. So yes, this is going to be the DO. Now, the flame of the candle is also the object. So this is the height of the flame. So this is the O. So how far away is the image forming? We are looking for the distance to the image. And how big does it look on the screen? That would be the height of the image. So first we're going to look at the die. And we say to myself, well, what formula has die in it? Both of them do. But which one has what we've got? And that, of course, we're going to say 1 over F is 1 over dou plus 1 over die. So if I'm looking for the die, the math here can be complicated because I have to find lowest common denominators and all that kind of fun stuff. Except we're going to cheat. Yes, there's a button on your calculator that says x to the minus 1. Some people's calculator says 1 over x. Those both mean the same thing, so you won't have both buttons. So if you have this cheating calculator, then all you have to do is, I'll show you. But all we have to, the only algebra here is to figure out how to get 1 over di by itself, because that's what we're looking for. So if I want to get this by itself, I say, hey, do and di are connected with a plus, so I'm going to move it to the other side with a minus. So I'm going to have 1 over f minus 1 over dou equals 1 over di. Now, how many 1 overs do I have? I have 3. So how many times am I going to have to use this button? 3 times. So I'm first going to put the f number, which is 8.9, and then I'm going to hit the x to the minus 1 button. Then I'm going to minus the dou, which was 9.1, and I'm going to hit the x to the minus 1 button. Then I'm going to hit equals, and that's going to give me 1 over di, but I don't want 1 over di, I want di, so I'm going to have to 1 over x the answer. So after I hit equals, I'm going to hit x to the minus 1 a third time. Notice I hit it 3 times. The biggest mistake that people have is they only hit it the first 2 times. They hit equals, and they say, wow, that's a really small number. It's because they didn't hit it that last time. So if you try that, you got
4.95.
Is that what you got?
Yeah.
Whoops. Equals. I got 404.95. So that'd be 405 centimeters, or 4.1 meters, 4.0 meters, whichever one you want to put it in. That all looks groovy. Now to find high, of course, we need to use the high over ho equals, stop it, di over dou. So if we're using this formula and we're looking for a high, then we need to move the ho. So she moves from down here to up there. So we end up with ho d over dou, which really sounds kind of goofy. Ho d over dou. Sounds like we're yodeling or something. So the ho, of course, was 3.2. A second ago we figured out the di was 405, and the dou, of course, was 9.1. So we made it much bigger. And again, if I just said how many times bigger did it go, then we would just use di over dou. We'd just say 405 over 9.1. We'd take out 40 times bigger. Those are easy, right? Yeah, we like easy math. Visual problems. How many people in here have a visual problem? That's most of us. Hey, we're all blind. We don't like you. We're gonna poke your eyes out.
Oh.
That'll teach you.
No, thank you.
If you are nearsighted, which is the most common problem, if you are nearsighted, you suffer from myopia, and your eye focuses in front of your retina. We correct this with a concave lens. If you are farsighted, you suffer from hyperopia, and your eye focuses in back of your retina, and we correct this with a convex lens. We also have problems called astigmatism and loss of accommodation. These are our four most common types of problems, and all of these we can correct with lenses, which is really nice. Now, like I said, if you're myopic, which most people are, your eye focus is in front of your retina. Now what happens is, again, your typical eye is shaped about like an olive, and you have a little lens at the front. Actually, you have a dual lens. You've got the cornea, which acts like a lens, and then right behind it you have a lens. But what's cool about the lens right behind it is there's a lens back here, and it's connected with little muscles. And normally, to focus something, what we need to do is move the lens back and forth. But I can't move the lens back and forth on my eyeball. So what I have to do is actually change the shape of the lens. So the lens is kind of squishy in there. And if I stretch it with muscles, then I stretch it and it becomes skinnier. And if I let it relax, it gets fatter. And so I actually change the shape of the lens, which changes the focal length of the lens. And you just keep doing that until it focuses right on your retina and you say, ooh, that looks sharp. And you're doing this all the time and you don't realize it. If I look at something close, I'm focusing here and you guys look blurry, and then I look back at you and you look sharp and now it looks blurry, and you're not even aware that this is happening all the time. You're constantly doing this. It's really kind of cool. So this is the way your eye looks normally, and what happens is light rays that come in nicely from something, they're going to focus right back here on your retina. There's an actual spot on your retina called the fovea, and that's the part that you get the critical focus on, and that's where it's really focusing on. Now, if you are nearsighted, your eyes are too long, and so your eyes tend to be shaped more like this, and so what happens is it's still trying to focus where it should, except your retina is back too far. So what we need to do is we need to put a diverging lens here. That's going to spread the light rays out. And if I spread the light rays out, then if the light rays come in here wider than they should, then they're going to focus back farther. And you say, well, how do you know exactly how much spreading out I need to do? If you've ever been to the eye doctor, you know. They practice with a bunch of different lenses. Which one looks better, this one or this one?
They also have machines that help you
Or
figure
this
out
one.
which ones.
This one or this one. And eventually you narrow it down, you say, that one looks good. And you say, hey, that was the right amount of correction. It's not terribly difficult math. On the other side, if you are farsighted, your eyeball tends to be too round. And so if your eyeball is too round, then what happens is the light rays that are coming in want to focus back here instead of there. So we solve this with the opposite way. We stick a lens that looks like this on it, and that's going to bring the light rays in farther, and if they converge the lens, then ideally they focus right where they're supposed to. So I bring the light in. So if you look at my glasses, I am nearsighted. When you see this, what's that doing to the light? Bringing it in or spreading it out? Hey, what do you know? It's diverging it. So if it's diverging it, then you can tell I'm nearsighted. Now, it's kind of funny, when you look at somebody and they're wearing glasses and you see their face through their glasses, it looks like I'm showing junior asparagus here. Yes. If your glasses have no correction at all, you would see the side of their face right there, right? But if their face moves this way in the glasses, that means they're getting smaller. The image looks smaller. And does an image look smaller with a convex or a concave lens? The concave lens can only form a smaller virtual image. So what happens is when you're looking through my eyes, what you see is my face gets made smaller through the glasses. And so if you look at somebody and their face looks really, really small through the glasses, you say, wow, you're really blind. And if you don't see much, then it's the other way. On the other hand, if you are a poor nearsighted or farsighted child, then you have one of these that's really close to your eye. If I'm inside F like this, it's a magnifying lens. If you've ever seen those kids where you see and their eyes look this big when you're looking through their glasses, the poor things are very farsighted. Now, astigmatism is when your lens is not equally round, like it's fatter over here and skinnier here and here. And so we correct this by doing the opposite. Wherever your lens is skinnier, we put a fatter lens, and wherever it's fatter, we put a skinnier lens, and so it averages them out. And loss of accommodation is what your poor parents are suffering from right now. Once you hit into your 40s and 50s, everybody starts handing you stuff, and you're like, what? Your parents ever do that?
My mom.
Yeah, and with me, since I'm nearsighted to begin with, I can see things up close, and so with me, I'm always doing this to read stuff, and it's, yeah.
What is it again?
And what loss of accommodation is we're just getting tired, man. I told you that there's little muscles in here that stretch your lens. Those muscles are just getting tired, and so it takes longer for you to adjust to the focus. And to do the near focus, you have to adjust more than the far focus. And so our poor eyes are just saying, forget it, man. It's not worth the effort. Yeah. So now you can become an ophthalmologist. You know everything you need to know. Right? For homework, of course, you want to do problem C, which means we skipped problems B, which we're just not going to have time to do. But first, I'd like to show you a cool demonstration, which hopefully we can get to before
The bell rings.
maybe.
13 minutes.